see everything. So thank you very much for the introduction, and great to be here with you this morning. So I would like to talk about deep learning on graphs from maybe a slightly different and exotic perspective compared to what many of you might have seen before. So maybe let me start a little bit from far away, and I would like to open with these two quotes. So the first one is from Hermann Weyl, one of the greatest mathematicians, mathematical physicists of the 20th century, who said that symmetry, as wide or as narrow as you may define it, is one idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. So the second quote is from Nobel laureate Philip Anderson, physicist, who said it very laconically that it's only slightly overstating the case to say that physics is the study of symmetry. And indeed, in the 20th century physics, symmetry has played a fundamental role, and nowadays, more or less every physics, maybe with the exception of gravity, can be derived exactly from these considerations of symmetry. Now, symmetry has played a crucial role in mathematics, starting with Felix Klein and his Erlangen program that unified different types of non-Euclidean geometries that existed around this time, and has shaped mathematics, at least on the principles, spinning it into also category theory and algebraic topology and many other continuations that became entire fields of their own. And in machine learning, the notion of symmetry has actually been recognized probably in the 60s in the famous book Perceptrons by Papert and Minsky that criticized perceptrons from the standpoint of proof theory. But I think it's fair to say that it has not been recognized until recently as an organizing principle, allowing to derive all these zoo of different neural network architectures, such as CNNs, GNNs, RNNs, transformers, from the same principles. And this is what exactly the geometric deep learning blueprint is approaching deep learning architectures from the standpoint of geometric priors, where you assume that your data lives on some domain that it has geometric structure described by a symmetry group, such as translation for images, for example, or permutation for graphs. Then this group acts on signals living on this domain, and then it is incorporated in the form of inductive bias or invariance or equivariance in the neural network architecture. And graph neural networks are a good example of a particular instance of this blueprint. As I said, the group assumption is a permutation. We don't have canonical ordering of the nodes in the graph, and then the functions that are implemented through message passing are equivariant with respect to the node permutation. And this blueprint can be applied to different domains, whether it's grids, meshes, or graphs. And what is interesting is actually all of these objects, maybe with the exception of graphs, can be considered as a discretization of some continuous space. So you can think of a grid as a discretization of the plane, for example, or a mesh as a discretization of a manifold. But it's not clear what is the discretization of a graph. And it is also obvious that graphs among all these objects have the least structure. So if you look at the grid, for example, I have canonical ordering of the nodes, right? So I know who is my nodes to the left and the node to the right. On the mesh, I have kind of canonical ordering up to rotation. So I have ambiguity in selecting the first neighbor, but after I do it, I can order all the rest in, let's say, clockwise orientation. On the graph, I'm bound to dealing with any arbitrary permutation of the nodes, and therefore they have least structure, right? So the kind of operations that we can define on the graph have to account for all these possible representations. And this is how graph neural networks historically has been designed. So you have a local function that aggregates features from your neighbors that exactly because of this ambiguity must be permutation invariant, and applying it at every point, at every node in the graph, you get a permutation equivariant representation. So it changes in the same way with the permutation of the nodes in the input graph. And it was shown, well, it has been known probably for many years, but recently it has become obvious in the graph learning literature that if you design the message passing function in a certain way, in particular make it injective, then the message passing graph neural network architecture is equivalent to Weiss-Perelman graph isomorphism test, which is a classical color refinement algorithm that has been developed in 1968 in graph theory. And this has become really more or less a golden standard in describing the expressive power of graph neural networks, asking what kind of functions or what kind of tasks can be solved by graph neural networks. So what I would like to show you today is a different perspective, and this is a good mental picture to have in mind for the rest of the talk. So we are talking about physical systems. So this is a figure from a paper recently published in Nature, where they incorporated real-world physical systems by backpropagating through them. So you can actually implement your deep neural networks with mechanical, electronic, or optical systems. And we want to do something like this. Well, obviously, in our case, it will be used more as a metaphor. So we're talking about some physical process or physical system that is described by differential equations, and by discretizing these differential equations, we'll obtain certain GNN architectures that also come with some theoretical properties and maybe theoretical guarantees, or at least a different perspective that allows us to revisit and rethink maybe some of the folklore statements about graph neural networks and what they can or cannot do. So the first thing that I would like you to consider is probably the most obvious kind of physical process that also has been studied, I would say, to death in the past at least 3 centuries, is the process of diffusion. So when we're talking about graph neural networks, it's fair to talk about them as a way of propagating information on the graph. So diffusion is a physical process that does exactly this. It propagates some quantity on a domain or in a medium. Let's talk about, for example, diffusion of heat. So we have certain temperature in our domain. The gradient of the temperature creates a flux of heat that is governed by what is called the diffusion equation. So it's a partial differential equation. On the left-hand side, we have the temporal derivative of the temperature. On the right-hand side, we have the divergence of the gradient. Basically, that captures the kind of conservation law that no heat is created or disappears. And there are multiple versions of the heat equation. So the simplest one is homogeneous and isotropic diffusion, where the heat propagates in the same way at every point of the domain. We can make it non-homogeneous by making the diffusivity position dependent, or anisotropic, making it also direction dependent. And these kind of equations have attracted a lot of attention in the image processing literature, where you can apply diffusion equation to, for example, denoise an image. So it will be averaging out the noise in the pixels, but at the same time, you don't want to destroy edges or discontinuities in an image that are important for visual perception. And the idea that dates back to Perona and Malik from 1990 was to make the diffusion adaptive. So it's driven by the gradient of the image, and the diffusion slows down or even stops completely when it encounters a discontinuity. So if you think of it, it's a very similar idea to attention, with the exception that it's not learnable. And this is what it does to an image. So we have the face of Sir Isaac Newton that is diffused by the standard homogeneous diffusion here in the center, and non-homogeneous non-linear diffusion that is edge preserving. So we can apply similar ideas to graphs, and this is how the diffusion equation will look on the graph. So we have the analogy of the gradient operator on the graph, which just take the difference between features at 2 endpoints of an edge. This is the diffusivity function that looks like an attention function, and in fact will recover attention type graph neural networks from this equation. And this is the divergence that aggregates all the information from the edges that emanate from the node. And we can discretize it. So the time variable here is continuous, so we can discretize it with fixed time steps using a numerical scheme that is called explicit or forward Euler iteration. And the updates of the quantity that we're diffusing, right, the node features, are given in this form, and we can recover the graph attention network as a particular case. So here, if you want to think of it in terms of neural network terminology, basically we are talking about each iteration being a layer of a graph neural network, and the diffusivity function is parametric. So we can learn it in a way that it solves a given task in the best way. And of course, we don't need to limit ourselves to explicit schemes. We can use, for example, implicit schemes that will require some feedback. We can also use multi-step schemes such as Runge-Kutta methods that are used classical in numerical analysis. So this will correspond to some form of residual architectures. And this framework that we call graph neural diffusion, or very modestly GRAN. So you start with some initial features on the graph, then you solve numerically the diffusion equation for a certain time with parametric diffusion function, and then you read out the obtained state of the system. And you optimize the parameters of the diffusivity function in a way that the task that you're trying to solve, such as node classification, is optimized. And this perspective gives a nice theoretical view on all problems. So first of all, you can explain existing architectures such as graph attention networks as a discretized graph diffusion equation, but it potentially also gives rise to more efficient solvers such as multi-step adaptive implicit multi-grid methods that do not have immediate analogy currently in the zoo of graph neural network architectures. You can also interpret, for example, implicit schemes as multi-hop filters. And also what comes from the theory of partial differential equations are different theoretical results, such as guarantee of stability and convergence, but also deeper links to other fields that are less known in graph neural network architecture, which is differential geometry and algebraic topology. And this is what I would like to describe. So this is really what excites me. Well, basically, my background is in geometry, so I like very much these maybe slightly exotic but deep and interesting connections. So far, when we talked about thinking of grids and meshes as discretizations of continuous objects, so we haven't yet achieved these for graphs, right? So we did have a continuous time in our diffusion equation, but the graph itself is still a discrete object. And if I go back to diffusion in the plane, for example, if I discretize the plane on the grid, then differential operators such as the Laplacian can be discretized in many different ways, right? So here I show three different possibilities of writing down a discrete Laplacian operator, right? And any convex combinations of these operators, because it is linear, would also be a valid discretization of the Laplacian. So the question is, can we do something like this for graphs? Essentially, get rid of this sacrosanct construction that is typically assumed in graph neural networks, the fact that you use the input graph to propagate information. So what I would like to advocate for is to say that the graph is a computational tool, should and could be detached from the input graph, and it should really be a numerical convenience. We propagate information the way that is best for a given problem. And I will give some examples why it is important. So here comes the differential geometric viewpoint. So we've seen this nonlinear, non-homogeneous diffusion equation, and basically it was this nonlinear diffusion equation. We can instead consider a non-Euclidean diffusion equation. So we now think of our image as a two-dimensional manifold, the surface that is embedded in some space, which now has joined set of coordinates. So we have the positional coordinates in case of image. These are positions of the pixels, and the feature coordinates like the color channels of the image. And we can pull back the metric from this embedding, define the metric on this surface, and write an equation that looks like the diffusion equation. So the only difference here is that the Laplacian operator is a non-Euclidean version, what is called the Laplace-Beltrami operator. And these kind of equations come from theoretical physics, from string theory in particular. So they are called the Polyakov energy or Polyakov functional. And basically this kind of equation minimizes this energy. So we have also a nice interpretation of a graph neural network as a gradient flow of certain energy that has certain meaning, kind of smoothness. So we can apply the same idea to the graph. In this case, we assume that every node that has two types of coordinates, it has the positional coordinates and the feature coordinates. And the positional coordinates, what is important is that they don't need to allow necessarily to recover the graph exactly from this embedding. So this can be basically some representation that is again convenient for the problem. And the embedding doesn't need to be necessarily in the Euclidean space. Actually, for many graphs, it's convenient to use, for example, spaces with hyperbolic geometry. And now we apply the diffusion equation to the pair of these coordinates. So this is what we call the graph Beltrami flow, and the evolution of the feature coordinates of X component is the standard feature diffusion that we see in graph neural networks, but the evolution of the positional encoding amounts to graph rewiring, because if we see that the positional coordinates of two nodes, for example, become closer, we can decide during this evolution to add an edge there to facilitate the propagation of information. And maybe this picture shows it in a way better manner. So here, this is a Cora graph, so one of the classical data sets that are used in graph neural networks. The color of the circles here represents some low-dimensional projection of the features. The positions represent some, again, low-dimensional positional encoding or positional embedding of the graph, and then the edges are changing as we evolve this data set. And you see that the colors are changing and the positions are changing and the nodes are clustered in this case, the task is a node-wise classification. So you see that this kind of representation is driven by the task that we are trying to solve. Now, if you think of this kind of viewpoint of evolution of features on the graph, that the graph itself is moving while you're doing this evolution. So if you find it somewhat disturbing, sorry, I think something happened to my slides. I don't know if you can still see them.
No.
Sorry, I apologize for that. Yeah, PowerPoint. What can I say? Do you see it now?
No, it's still black. Let me make you once again as a presenter and you will share. Maybe something happened.
Yeah, let me do it again. Sorry, guys. This unfortunately happens. Can you give me again the okay. Yeah, hopefully you can see it now. Yeah, so basically this setting where you have a domain that is evolving and changing under your feet, where you're doing something on this domain, might be quite exotic for people working on image processing or signal processing or machine learning, but it is standard in differential geometry, and probably the most famous of all these evolution equations that are applied to a domain or a manifold are the Ricci flows. So you can see the equation here. So it's sometimes it's called the diffusion of the Riemannian metric. So we change the Riemannian metric driven by the curvature of the manifold. So structure is similar to the diffusion equation. The properties are very different. And it is actually a big deal in differential geometry. It's used as an analytical tool. And one of the celebrated applications of it was the proof of the Poincare conjecture that was proven by using this technique of Ricci flows. So in our case for graphs, why would you at all bother to consider something like this? So one of the common problems that you encounter in graph neural networks is the problem of oversquashing and bottlenecks. And what it is essentially when you have graphs that have exponential volume growth. So you have a lot of neighbors as you go to the neighbors of the neighbors. So the number of neighbors becomes very large. And your task depends on long distance information. So what you get is that you have a lot of information to squeeze into a single feature vector. And this is a phenomenon that is called oversquashing. And it's not unique to graph neural networks, but graph neural networks are the case where this is probably the most dramatic. Now, the way that you can think of oversquashing in graph neural networks is a kind of sensitivity problem. So if I have a graph neural network with several layers, and I'm looking at the output at some node, let's say node I can check how it depends on the input at some distant node S. Okay, and I can write it as a derivative, a Jacobian. And if this derivative is small, it means that my output is insensitive to the input. And we show that we can bound it well by the Lipschitz constants of the message passing functions, but also it depends on the structure of the graph in some implicit way through the power of the adjacency matrix of the graph. Now, we obviously know that in some graphs, this phenomenon will be more acute than in others. So trees are, for example, the pathological example where this insensitivity, right, or oversquashing is the hardest. And in grids, for example, this will probably be a much less of a problem. So in differential geometry, a construction or a notion that allows you to distinguish between objects that look like grids, right, or like planes, and something else is exactly the curvature. So you can associate it with what is called geodesic dispersion. So if I take two points and I shoot geodesics from them, I can see whether they will converge, remain parallel, or diverge. And this differentiates between spherical, Euclidean, and hyperbolic geometries. So something similar can be defined on graphs. So I can take two nodes that share an edge, and I can look at the edges that emanate from these nodes, and I see if they form cliques. In this case, we're talking about something that looks like spherical geometry or elliptic geometry. If they remain parallel, so they form rectangles or look like a grid, so this is kind of flat geometry, or if they diverge and form tree-like structures, in this case, we're talking about hyperbolic behavior. And we can define a curvature, allow me to skip the details, that reproduces the behavior of the continuous Ricci curvature. So it will be positive for cliques, 0 for grids, and negative for trees. And what we show is that if we have a graph, basically we can relate the oversquashing, this Jacobian that we've seen before, that tells us how the output features depend on the input features. We can attribute the small Jacobian to negatively curved edges in the graph. So in other words, negative curvature is bad for information propagation in graph networks. And once we know it, we can cure the graph. We can do some form of rewiring that resembles the Ricci flow, where we cut out the negatively curved edges and maybe replace them with edges with larger curvature. And this allows to do the kind of surgical graph rewiring that doesn't change dramatically the structure of the graph, but makes the graph significantly friendlier for message passing and as a result for learning. And especially it is more prominent in heterogeneous settings, heterophilic settings, where the features or the labels of neighbor nodes can be different from the feature label of the node itself. Now, last thing that I would like to mention, talking about exotic things, I hope that it didn't sound too exotic. So here is a construction from algebraic topology that is called sheaves. And basically, if you think of a graph as an analogy of a manifold, right, or a discrete version of a manifold, it is a topological object in the sense that you have a notion of connectivity, but you don't have notion of geometry or distance or angle. And same thing about manifold. So if you want to equip a manifold with geometry, you define a notion that is called parallel transport or connection that allows you to move vectors from one point to another, or more correctly, tangent space at two different points, adjacent points in the manifold. So cellular sheaf is a kind of similar construction. So we can equip every node with an edge with a vector space. And we have what is called restriction maps. So these are linear maps that allow us to map information from one node to another. And basically it allows us to equip the graph with geometry that if we consider a diffusion equation on such a construction, it has much richer properties, and it can avoid certain phenomena such as oversmoothing or problematic behavior in case of heterophilic data sets. And basically we can look at the limit of the diffusion equation on the sheaf with some initial conditions and pose those classification as whether in the limit we can separate certain node classes. So, and you can think of it in terms of expressive power. This is a different approach that doesn't stick to the classical Weisskor and Lemon hierarchy and basically considers a different process, a physical process on the graph, maybe with this exotic geometry that allows us to reason about the expressive power of graph neural networks. And what we show, so this was a recent paper that we authored that basically studies different classes of sheaves and how they affect the expressive power of graph neural networks. So the last thing that I would like to ask is maybe more a provocative question is, are we done at this point with message passing? So message passing as a computational paradigm has been around for forever, more or less since the birth of the digital computers, and graph neural networks conveniently use message passing as a computational paradigm. So the question is, what we are doing here, is it beyond message passing? So I think to some extent it is, and maybe as an implementation we'll still be resorting to message passing, but it will inform the right architectural choices. How, for example, to design the message passing functions. For example, we see that orthogonal message passing has many advantages, both computationally and theoretically. So just to conclude, I think that the physical or geometric or topological perspective on graph neural networks brings completely new set of tools that allows, first of all, to understand how graph neural networks work, why they work, and when they don't work. And this will hopefully give birth to new architectures that will be more expressive, more explainable, more lightweight, and so on. So I will stop here. Thank you very much. We'll be glad to answer any questions. Well, obviously, you can feel free to contact me either by email or Twitter or well, any other social network or messaging. I will try to answer any question that you might have. So I think there is a question. Yeah. So this allows us to inject elements of reason into the model to allow physical interpretation from the clustering that results. Well, so two things. So the physical interpretation, first of all, gives some interpretability or explainability to the graph neural network. Well, it's a little bit an abused word, so and it's in the eyes of the beholder. But what I didn't show, but that was implicit in what I was presenting. So differential equations that we discretize to get graph neural networks are actually gradient flows or minimizing flows of some energy functions. So basically, I can say that graph neural network minimizes something that has clear physical interpretation, something like the Dirichlet energy for the case of diffusion, or the Polakov energy for the case of the graph Beltrami flow. So this is on the one hand. On the other hand, I can incorporate multiple assumptions about my problem, different conservation laws or different symmetries, different restrictions. So in case of shift diffusion, for example, I can say that I consider only orthogonal transformations, which of course restricts the number of parameters. So it makes the neural network much more lightweight and obviously then more efficient in terms of the amount of data that they need to train on. And also you understand better, so you can analyze its behavior, for example, by looking at the limit of this diffusion. So there is a question, another question, are there Python libraries that are available for public to use and play around with these things? So the question is yes. So with graph neural networks, there are multiple libraries. So one of them is PyTorch Geometric, another one is DGL, Deep Graph library. But specific implementations of, for example, neural diffusion PDEs, you can find it on GitHub. So we have releases with our papers.